Welcome to Chapter 7. This is a chapter on computer arithmetic. We shall use all the knowledge that we have gained in designing digital logic, all the knowledge that we gained in Chapter 2, the language of bits, to design circuits in this chapter to implement adders, multipliers, and dividers. So, this is Chapter 7 of the book Computer Organization and Architecture, published by McGraw-Hill in 2015. So we have these 6 parts in this chapter. We have addition, multiplication, and division. So these are integer addition, multiplication, and division. And then we have floating point addition, multiplication, and division. So the entire chapter is broken down into 6 sections. So let's take a look at the simplest problem, which is to add two 1-bit numbers, A and B. So if we add two 1-bit numbers, what is it that we can get? The largest number that we can get will actually require 2 bits. So let's see how and why. If we add 0 and 0, so let's assume the output is 2 bits. So the output is 0, 0. If we add 1 and 0, the output is 0, 1. Similarly, if we add 0 and 1, the output is 0, 1. And if we add 1 and 1, the output is 1, 0. So 1 plus 1 is 2, and the representation of 2 is 1 and 0. So what we see is that for the first 3 results, 1 bit is sufficient. For the last result, we need 2 bits. So pretty much we can say that we add two 1-bit numbers. The final result can take 2 bits. So it's better if we allocate 2 bits. So the least significant bit of the result so it's a 2-bit result, right? So the least significant bit, which is let's say this bit, is known as the sum, and the most significant bit is known as the carry. So we shall see why. If we add 0 and 0, the sum is 0, nothing is being carried. Same is true for 1 and 0 and 0 and 1, but we add 1 and 1, 1 plus 1, then so if you do a binary addition of 1 and 1, so what do we get? So what we would get is that essentially the unit's position, the least significant position will be a 0, and we'll be carrying 1 to the next position. So basically the carry will be 1 and the sum will be 0. So 1, 0 in decimal is 2. Alright. So let me give you some more examples of, let's say, binary additions. We would do it exactly the same way as we do in base 10, and we can take a look at the carry business in some more detail. Let's assume it's 1011 plus 0010. So 1011, if you consider it to be an unsigned number, it's 11 in base 10, and 0010 is 2 in base 10. So if we add, it should be 13 in base 10. So 1 plus 0 is 1. 1 plus 1 is 2. In binary, it's 1, 0. So the sum is 0 and the carry is 1. So the carry goes to the next position, this position. So 1 plus 0 is 1. And we again have 1. So what is the sum? It is 8 plus 4, 12 plus 1, 13, which is exactly what we would expect. So addition in binary is exactly the same as addition in base 10. There is no difference at all. And in base 10, we also carry a 1. So let's say I was to do the similar kind of an addition. Let's say in base 10, which would maybe be something of this type. So 2 plus 9 is 11, I write 1 and then I do a carry. So it's 1 plus 5 is 6 plus 2 is 8 and 7 plus 1 is 8. So the same way we do a carry in base 10, we do a carry in base 2 as well. And so in the case of a 1 bit, we call the least significant bit as the sum and the next bit as the carry. If I draw a simple truth table of what are the values of A and B and what is the sum and carry, so we see if A and B are 0 and 0, the sum is 0, the carry is 0. If A is 0 and B is 1, the sum is 1 and carry is 0. Likewise, if A is 1 and B is 0, the sum is 1 and the carry here is 0. And lastly, if A is 1 and B is 1, the sum is 0 and the carry is 1. So the sum is LSB, mind you, and the carry is the MSB. So what we can see, if we want to implement this in a Boolean system, we can see that the sum bit over here is actually A XOR B. So why is this the case? So basically, if 0 and 0, the XOR of them is 0. 0 and 1, the exclusive OR is 1. 1 and 0 is 1. And if 1 and 1, it's 0. So we can say that this is this function. So go back to chapter 2 again for an explanation of this. Is the exclusive OR operator, which can be expanded to this, where the plus sign is denoting the OR operation and the dot sign is denoting the AND operation. So it's essentially A complement and B or A and B complement. So that is the sum, and the carry will happen in only one case, when both A and B are 1. So we can see it is A and B. That is when we'll have a carry. So we can then implement a simple Boolean circuit called a half adder, which adds to 1-bit numbers to produce a 2-bit result. So in this case, we'll add A and B, and the result will have a sum and a carry bit. So we just need to implement the circuit, the Boolean formulae showed over here. So what we see over here is that this particular formula needs to be implemented. So we take A complement, we AND it with B, and the other had A and AND it with B complement. After two AND gates, we compute an OR function, and this becomes the sum. And the carry was anyway A and B. So what we do is we pass A and B via an AND gate, and the result is the carry. Let's now consider a full adder. So basically, full adder will be required when we want to add 3 bits, and here is when we'll need to add 3 bits. So let's assume that there is a large Boolean number, right? Something of this type. So in this case, when we perform the addition for the first, we can, for the LSB bits, we can use a half adder. So it will produce a sum of 0 and a carry of 1. So mind you, for the second position, we are actually adding 3 bits. We are adding 1 plus 0 plus 1, right? So this will produce a sum of 0 and a carry of 1, but essentially a full adder will be something that takes 3 bits as input. So if you take 3 bits as input, 1 plus the largest possible sum that we can have will essentially be 1 plus 1 plus 1, which is 3. Is binary representation is 1 and 1, so 2 bits are sufficient. So in this case, a full adder will have 3 inputs and it will have 2 outputs. So in this sense, 2 bits are sufficient to get the outputs. So what we can say is that the 3 input bits can basically be called A, B, and a carry in. So in this case, the first number here can be called A, this number can be called B, and there is a carry which is actually coming from the right, so this can be called the carry in. Then what will be the output? The output will be a sum, the sum S, and we'll have a carry as an output, and to differentiate that from carry in, let's call it carry out. Alright, so there are 3 bits coming into a full adder, which is A, B, and carry in. if you're adding two if you're adding two multi-bit binary numbers, so A will be, let's say the ith bit of one number, B will be the ith bit of the second number, and carry in will be the carry that is coming in from the right, and the outputs will be the sum and the carry out. So the number will be equal to 2 times carry out plus S, a simple binary expansion. And this is what a truth table will look like. So if A, B and carry in are all zeros, so naturally sum and carry out both are 0. Similarly, if A and B are 1, 1 each, carry in is 0, it's 0 and 1. So a reader just needs to verify all the entries in this table and ensure that they are correct. So let's take a look at the last entry. So this is the sum A, B and carry in are all ones. So 1 plus 1 plus 1 is 3, or 1, 1 in binary. So sum is 1 and the carry out is 1. So what are the equations for the full adder? Let's take a look at this. So the sum, if you take a look at the sum, let's again go back. So essentially in the sum, if so when is the sum equal to 1? The sum is equal to 1 when B is 1 and A and carry in are 0, or when A is 1, or when carry in is 1, the rest two are 0, or when all three are 1. So what we can see is that the sum is 1 only when, if and only if, out of A, B and carry in, an odd number of them are equal to 1. Right? So basically, in this case, B is 1, the rest are 0. In this case, A is 1, the rest are 0. In this case, C in is 1, the rest are 0. Or all three of them are equal to 1. So typically, any such function for the sum can be represented like this as A XOR B XOR carry in. So this will be true only when an odd number of A, B and carry in are 1. So either one of them is 1, the rest are 0. So 0 XOR 1 is 1. Or when all three of them are equal to 1. So basically 1 XOR 1 XOR 1 can be thought of like this, that 1 XOR 1 is 0, and then 0 exclusive OR with 1 is 1. So we can just do a simple algebraic expansion of this. We can take, since the rule of associativity is followed, we can take A XOR B and expand it to A and B complement, or A complement and B, and just keep on expanding it. So finally, if we do the algebra, this is the final result that we get. So in this expression over here, what we see is that when will this be true? So this expression will be true when A is 1, both B and the carry in are 0. Similarly, in this expression, this will be true when B is 1 and both A and the carry in are 0. And similarly for this, so this takes care of the first three cases, and the last case will happen when the last case will be true when all three of A, B and the carry in, all three of them are equal to 1. So this is exactly what we have in this truth table over here. This is exactly what we are trying to capture. Now let's come to the carry out. So when is the carry out equal to true? So the carry out is equal to true when A and B both are 1, carry in is 0. When B and carry in are 1, A is 0. Or A and carry in are 1, or when all three are. So essentially the carry out is true when at least two of A, B and carry in are equal to 1. So this can be nicely captured in this thing. Let me just summarize. When is carry out equal to true? Carry out is equal to true when at least 2 out of 3 of A, B and carry in are equal to true. So this will become so the way to express this is, if A and B are true, then A and B, this expression will be true. If A and carry in are true, then this will be true, or this expression will be true. So essentially, if these three bits, any two of them are true, at least one of the conditions here should be true, and thus carry out will be equal to 1. Otherwise, carry out will be equal to 0. So for creating a full adder, we basically need to create a circuit that will realize these Boolean equations in hardware. So this is the circuit of a full adder. Looks complicated, but it's not complicated. So carry out is slightly easier to understand. So carry out is A and B, or A and carry in, or B and carry in. So what we can see is that this is A and B. This is A and carry in, and this is B and carry in. So for what we do is that we have three AND gates and we have an OR gate whose output is carry out. Now let us consider the sum. So in the case of the sum, what we need to do is we need to figure out the values of each of these expressions. So let's consider the first one, A and B complement and complement of carry in. So this will get captured like this. A is coming here. Then I'm sorry, yeah, this one. A is coming here, so this is A. This value is B complement, and this value over here is the complement of carry in. So this is getting captured over here. So the output is A and B complement and complement of carry in. Similarly, the rest of the two AND gates are capturing the rest of the two terms, which are this and this. And we need one AND gate to capture this term, which is A and B and carry in, which is the first AND gate, where we are just computing the AND other values. And at the end, to compute the OR, we have a 4-input OR gate. So this gives us the sum. So computing the sum is more difficult, requires more hardware as compared to computing the carry out. But this is pretty much the circuit of a full adder for you, which takes 3 bits as input, adds them, and there is a 2-bit output. For the LSB, the least significant bit is the sum, and the most significant bit is the carry out. So both of these are getting computed in this fashion. Let us consider the addition of two n-bit numbers. So the way that we start is we just, so these are two n-bit binary numbers. The way we add them is exactly the same way as we add base 10 numbers. So we start from the right and move towards the left. So we first add the first pair of numbers, and so if we add the first pair of numbers, what we see is that we add 1 and 1. So 1 plus 1 is 1, 0. So we have 0 as the sum bit, and we carry over 1 to the next position. In the next position, we need to add 1 plus 1. So again the sum bit will be 0, and again we'll carry over a 1 to the next position. Again we add 1 plus 1, so the sum bit is again 0, and we carry over 1. So we have 0, and finally we again carry over a 1 to the next position, and the addition completes. So the final result is 1 and 4 zeros. So what do? We start from the least significant position. We start from the LSB. Then we add the corresponding pair of bits and the carry in, and we produce a sum and the carry out. So the carry out pretty much at the ith position is the carry in for the I plus 1th position. So some quick observations are due. So we need to keep adding the pairs of bits and proceed from the LSB to the MSB. If a carry is generated, we add it to the next pair of bits. And at the last step, if a carry is generated, then so if you see here in the last step a carry is generated, so it essentially becomes the most significant bit, the MSB of the result. So the carry effectively ripples through the bits. So let us first design a very simple adder called a ripple carry adder. So in this case, we'll add two multi-bit binary numbers A and B. So let's assume that they have n bits each, and the bits are A1 to AN, right? That's the addition that we do. Plus, so Bn means the nth bit and B1 means the first bit. So when we add, we'll first add A1 and B1. So mind you, there is no carry input, so we can use a half adder. So the half adder will produce a sum bit and it will produce a carry. Subsequently, we need to add A2, B2 and the carry that was generated. So we need a full adder. So again, we save the sum bit over here and we move the carry to the next position. So here also we use a full adder and we add A3, B3 and the carry. So in a similar fashion, we go till the nth position, which is the last point. We add the carry AN and BN. So finally we have a sum bit and we have a carry out. So since we have nothing more to add, the carry out becomes the most significant bit of the result, right? So this is this carry out, the bit that comes out. So this is exactly the same as the addition that was done over here. The only important point to note here is that at the least significant position, we have a half adder because there is no carry input, and the rest of the adders are full adders. So this particular adder, let me actually go back once again. This is called a ripple carry adder because essentially the carries pass from one adder to the other. So it's like a ripple, it's like a wave of carries going from right to left. So in this problem, what we are essentially doing is so this is sort of a textual description of what I described on the previous slide, that we start from the right and we gradually move to the left and we keep on adding the carry values. So how long does the ripple carry adder take, right? So the question is, when we design an adder, we should know how long it takes and to perform the addition, such that we can, when we compare two adders, we can compare them on the basis of the time. So let us assume that the time a half adder takes is th and the time a full adder takes is tf. So as we see, the total time that this adder will take, let me go back, is essentially the time for one half adder to compute its carry, and then since these are in series, it will be th plus n minus 1. In an n bit addition, we'll have n minus 1 full adders. So it will be th plus n minus 1 times tf. So let me now define the notion of asymptotic time complexity, which is very, very important in computer science. So most of the time we are primarily interested in something called the order of the function. For example, let's consider this expression 2n square plus 3n plus 4. So if we take a look at it, well, 3n is important, 4 is important, but consider n is a fairly large value. So the only term that actually dominates this expression is 2n square. So the rest of the terms, in a certain sense, can be ignored. Again, it's being mathematically inaccurate, but we shall see that there are some advantages to this. So basically these terms can technically, well, not technically, but in a certain sense can be ignored. And so basically, even let's say the constant 2n square, we can, while broadly thinking of the approximate time, we can even ignore the constant 2, and we can say that this function sort of grows as n square, right? Ignoring constants. So it is possible to say that a function of the form 2n square plus 3n plus 4 is the order of n square. And the reason it is possible to say this is because we have decided to get rid of constants. And so if we see, maybe the graph of this function will essentially be a quadratic graph. might be something like this, and maybe n square will sort of be half of it, it'll be something like this. But pretty much, we sort of want an approximate representation where we don't want many constants. So we can say that, look, as long as two curves are uh, sort of one curve is a multiple of the other curve, right? It's some constant times another curve. We'll ignore the constant. So we can say that this is approximately growing as n square would grow. So let us try to formalize this notion. So let me introduce the big O notation. So this notation is called big O, capital O. So formally we say that a function fn is order of, so big O of gn, if fn is less than equal to a constant times cgn for all n greater than some n0, where c is a positive constant. So let me, I'll explain it with an example, but let me say what this means in a slightly colloquial sense. So let's consider two functions, fn and gn. So let's say this function is the same old function, 2n square plus 3n plus 4. And we are saying that this is order of n square. So what this basically means is that we can say that 2n square, so let's consider positive n, so the absolute value will go away. So anyway, the absolute value is more of a mathematical artifact. We can say that this is, less than equal to 10n square for n greater than 100, right? You can definitely say that. That this is less than this. In this case, c will be equal to 10 and n0 will be equal to 100. So it can be said that this function 2n square plus 3n plus 4 will essentially grow the same way as n square will grow, ignoring constants. So let's look at another example. So in simple terms, what we are saying is that beyond a certain value of n, gn is greater than or equal to a certain constant times fn. For example, beyond 15, n square plus 10n plus 16 is less than equal to 2n square. So in this case, we can say n0 is equal to 15 and c is equal to 2. Now let's consider an example of the big O notation. So let's look at fn is equal to 3n square plus 2n plus 3, and let's find its asymptotic time complexity. So fn is 3n square plus 2n plus 3, which is less than equal to 3n square plus, well, 2n is less than 2n square when n is greater than 1, and 3 is also less than 3n square when n is greater than 1. So if I sum up all of these terms, fn is less than equal to 8n square. So what can be said is that fn is actually order of n square, where the constant n0 is equal to 1 and c is equal to 8. So if we plot the graphs, we'll notice an interesting thing, that after this point 1, right, which will roughly be here, we can see that fn is clearly greater than, I'm sorry, 8n square. So 8n square is this green curve over here and fn is the red curve. So we can see that 8n square is clearly greater at all points as compared to the original function fn. So we can say that 8n square is a strict upper bound on fn as shown in the figure. So essentially the point is that we can have any kind of function with any number of polynomial terms. We want to find a simple upper bound and ignore multiplicative and additive constants. So the order notation pretty much gives us a mathematical tool of achieving that. For example, let's consider this function 0.0001 n to the power 100 plus 10,000 times n to the power 99 plus a big constant. Let's find its asymptotic time complexity. So it is true that this coefficient is very small and this coefficient is very large, But definitely we can find a value of n at which, this term will dominate, right? So, keeping that in mind, we can use the same algebraic formula listed in the previous slides and essentially say that fn is order of n of 100. See, pretty much we have to take the highest exponent while computing the order of a function. So in this case is n to the power 100. Why is this the case? Because we can always find, say if this is fn, right? We can always find a constant c such that c is less than n to the power 100 for a certain n greater than n0, right? So basically we can always find something of that nature. So one thing is, if I set c as 10,000, so 10,000 n to the power 100 is more than this term, but again these two terms will increase. But that's okay. If I keep on increasing the value of n, ultimately I'll find out some value of n0 and c such that this function is strictly less than c n to the power 100 for all values of n. So hence we can say that fn is equal to order of n to the power 100. So one simple way is that if it's a polynomial expression, take the highest power of n, right? So that is the order of the function. So we shall essentially use the big O notation, which is actually very easy and uh, it's very easy to use and very easy to compute to characterize the time taken by different types of adders. So let me talk about some issues that students typically raise. So students might say that, look, we might have a function of this type. Let's say 0.1 n square plus 300 n plus 20. And so in this case, for a lot of values of n, pretty much this term will dominate. So the question is it still order n square or is it order n, and how do we use it to compare? So the question is that, so the big O notation is an approximate representation. Is sort of telling you that a function for sufficiently large values of n is bounded by another function uh, after taking multiplicative constants into account, right? So basically, it's all that it's saying is that, look, if you have a function of maybe this type, then this is bounded by some other function of this type, right? So it's sort of finding a boundary of the function. So this function, if this function is fn, this is something of the form c times gn, right? That's what we are saying. And so when you are saying that fn is order of gn, this is exactly what we are trying to say, that we are sort of creating an envelope for the function such that fn is less than the envelope at all points. So this has some value in the sense, of course, the value of n matters, the multiplicative constant matters. Essentially, the value of n0 and c definitely matter, right? There's no doubt about that. But still, it gives us a good idea, and it is very unlikely that in real life, if you have one function whose asymptotic complexity is higher than that of another function, then it will actually be faster in practice. So that typically does not happen. In a sense, an order n time algorithm or a circuit, right, is typically much faster than order n square. Of course, I mean, there might be more constants in this equation which are getting ignored, but typically it's the case that an order n time algorithm is much faster. So let's take a look at the complexity of a ripple carry adder. So let's actually go back. So at this point, what we see is that the time complexity is th plus n minus 1 times tf. So basically these th and tf are constants. So the only variable in here is n, and so we can say that this is equal to order of n, where n is the number of bits that we are trying to add. So the complexity of a ripple carry adder thus becomes order of n, in the sense that asymptotically, roughly we will take order n steps if we have n bits. If it's a 32-bit addition, roughly we'll take some k times 32 steps, and if it's a 64-bit addition, we'll roughly take c times 64 steps. So the question is, can we do something faster? Can we do something which is much better than order of n? That's the question that we need to ask. Well, the answer is yes. So let's look at a carry select adder which takes order of square root of n time. So let's do one thing. Let's group bits into blocks of size k. So if you're adding two 32-bit numbers a and b and k is equal to 4, then the blocks are, so what we'll do is we'll group them into blocks. So we'll consider 4 bits at a time, a1 to a4, b1 to b4. Then we'll add them. A carry will propagate across the blocks, same way a carry will propagate. And for each block of bits, 4 and 4, we'll produce the result of each block with a small ripple carry adder. So we'll have separate ripple carry adders for each such small block. So in this case, what will happen is that instead of treating adding a bit at a time, we'll be adding 4 bits, entire block at a time. So the carry will then propagate across blocks, which will still take order of n time. But let's come up with a novel idea of how to speed it up, right? So what was the original aim? The original aim was that from an order n time complexity, we want to move to a order of square root of n time complexity. So here is what we want to do. Let's do one thing. So let's consider the structure of the addition, right? So what have we done? We have essentially divided the numbers into blocks of 4 bits. So let's consider one block. So what is the inputs? What are the inputs to the block? The input to the block is the carry input from the previous block. What is the output from the block? The output from the block is the carry from the block, right? So these are the two inputs and outputs. There is a carry in and there is a carry out. If we know the value of the carry in, we can perform the addition correctly. So let's consider any block. So what are the possible values of carry in? They are either 0 or 1, right? Only two values of the carry in can be there. So what we can do, so here is the brilliant idea behind the carry select adder, right? So this is very important. So what we can do is that for each block, we can actually produce two results, right? So when you are doing the addition, you can actually produce two results, result 1 and result 2. So basically when you are adding two numbers, so let's say we're adding two blocks of numbers from a4 to, let's say, well, a4 might not be the right example. Let me just maybe delete it. Let's say that we are trying to add a12 plus so for this particular block, the value of the carry input can either be 0 or 1, right? So we don't know that. So let's first assume the carry input is 0 and let's produce an output. So the output will have 5 bits, 4 of them are sum bits and 1 of them is the carry out. Then in parallel, what we can do, so since it's in hardware, right, we can do a lot of computations that are in parallel, right? So there is no need of doing one after the other. In parallel, what we can do is that we can perform another addition for the two blocks assuming that the carry in was actually 1. So that will also produce its result and a carry out. Alright, so what we can do is that for each block we produce two results. We assume an input carry of 0 into the block, so we produce one result, and we produce one more result by assuming an input carry of 1. Both of these, since it's in hardware, both of these can happen in parallel. Right, so for what we can do is that for each block, so assume that we are adding to 32-bit numbers and we have blocks of size 4, so we'll have essentially 8 pairs for 8 blocks. For one block, we'll have 2 pairs of 4-bit numbers, right? So for each block, we actually produce 2 results. The first result assumes that the input carry coming from the previous block is 0, and the second result assumes that the input carry coming from the previous block is 1. The result will have the sum bits and a carry out bit. Now, so what we have for, let's say, two 32-bit numbers that we are trying to add, a plus b, we have a sequence of 8 blocks, right, where each block has 4 bits. So we can generalize it. Let's say each block has k bits, and that's also fine. And so they are supposed to be equal size rectangles, sorry. And so then essentially what we can do at this point, so in stage 1, what have we done? What we have done is that we have, for each block we have done the addition, assuming an input carry of 0 and an input carry of 1, so we have 2 results. In stage 2, what we do is we start at the least significant block. So clearly the input carry into this is 0. So then we quickly choose the appropriate result from the first stage and again send, so the result will have the carry out. So we again send the carry to the next block. Then we quickly choose the appropriate result from the first stage and send the the appropriate carry out to the next block, and so on and so forth. So how long does this process take? So let's first find out how long did stage 1 take and how long does stage 2 take. So let's assume that each block has k bits. So we are essentially doing the additions in all the blocks in parallel, mainly because there is no carry business, right? We are assuming a carry of both 0 and 1. And each block, since it has k bits, we can use a ripple carry adder. So that will take order of k time. And in this case, what we do is we start at one block. So we quickly decide which output it is. We send the carry. Let's say the carry here is 1. Then in the previous stage, we have already computed 2 results. So we choose that result which corresponds to an input carry of 1. Then we quickly propagate the output carry again and again and again. So we can say that in each stage it roughly takes constant time, which is order 1. And since there are, each block is k bits, right? So basically there are n by k blocks. So we can say that the entire operation takes order of n by k time units. Alright. So, what again, let me just summarize what we do in stage 2. Given the result of this, let's say the nth block, in this case the second block, we compute the carry in for the third block, which is very easy. We just take the carry that is coming in. So let's say for the second block, for block number 2, we know the carry in. Since we have the pre-computed results, we can immediately find what is the carry out. And then this goes to the next block, the third block. And since again we know what is the carry in, we can choose from one among the 2 pre-computed results and send the carry out and so forth. So in this manner, we proceed till the last block. At the last block, we choose the correct result, and basically this finishes the entire computation. So how much time did we take in doing this, right? So since our block size is k, as I said, stage 1 roughly takes order k units of time. And so this can be k times some constant, it does not matter. So that's the reason I have removed it for the sake of simplicity. But the reader is encouraged to assume it takes c1 times k time. And so the constants don't matter, they'll get factored out in our equation. So for the sake of simplicity, let's assume that stage 1 takes k units of time. Since there are n by k blocks, stage 2 will take n by k units of time. So total time is k plus n by k. So what is k? K is the block size, a number of bits in one block. So let me write it down. K is the block size and n is the number of bits that we are trying to add. So n is clearly cannot be changed once the problem is given to you, but the block size can be changed. So let's do one thing. For finding out the minimum of this function, let's differentiate it with respect to k. So whenever the derivative is 0, we'll be able to find a maxima or minima. So in this case, we want to minimize the time, so we want a minima. So let's differentiate it with respect to k. So it becomes 1 minus n by k square. And so the optimal value of k for which the total time is minimized is actually square root of n. That's a very, very important point to take into account, which means that let's say if we have a 32-bit addition, right? We're adding two 32-bit numbers. So square root of 32 is between 5 and 6. So any of the numbers are fine. So what we essentially need to do is that we need to create 5-bit blocks of numbers. So let's say A5 to A1. Similarly, A6 to A10. And similarly, we need to add these blocks and use a ripple carry adder. Use a carry select adder to add these pairs of blocks. So that will give us the fastest possible time. And what is the fastest possible time? So it's essentially k plus n by k, when k is equal to square root of n, becomes square root of n plus n divided by square root of n, which is 2 times square root of n, which can be written in an approximate notation as order of square root of n, because all additive and multiplicative constants are ignored. So pretty much what we have achieved in our carry select adder is that we have created an adder that takes order of square root of n time, and so which is fast. We thus have a root n time adder. So basically, how fast was a ripple carry adder? The ripple carry adder, which was very, very simple, took order of n time, and the carry select adder takes order of square root of n time. So it is expected to be much faster. So mind you, as I said, it is not necessary that for relatively small values of n, any function which is order of n is actually slower. In the sense, I can always give a pathological example. I can always give a pathological example that consider this function, which is an order of n, versus consider this function. For most values of n, actually this function is smaller. But this is a very, very pathological example. It's typically not the case. So even if, I encourage students to actually implement the carry select adder in hardware and see for themselves, find out for themselves that it is genuinely faster than the ripple carry adder. I mean, asymptotic time complexity definitely gives you a broad direction that yes, maybe it is faster, but also you can implement it in hardware and see that it is faster. And definitely, as you increase the number of bits, 64, 128, and so on, the carry select adder is definitely much, much faster, as can be seen from the asymptotic complexity as well. Now let's ask our magic fish, can we do better? Well, Magic Fish says yes. We can do better. We can do much, much better. In fact, so how much better can we do? Right? That's the important question that we need to answer. Let's now consider the carry lookahead adder, which is much faster. So we'll roughly do it in order of log n time, so which is significantly faster as compared to n and square root of n. So let's first take a look at the insights. So since since this adder is much faster, and also this is the adder that is used in most commercial processors, it is also far more complicated. So we need to take it slow. So let's first take a look at the main insight. So the main problem in addition is the carry, right? So the carry is the one that goes from one block to the other, and that is essentially the sequential bottleneck. Otherwise, in hardware, if we can do things in parallel, then things will be much faster, right? So if we take a look, so basically, where did the speed up in the carry select adder come from? It came from the fact that in stage 1, we can treat each block separately in parallel, right? So essentially, we can treat all the blocks simultaneously. We assume we don't know what's the carry, but we produce two results, so we do extra work, and we produce two results for an input carry of 0 and 1. So that is stage 1. Then in stage 2, the carry quickly ripples, and instead of rippling across bits, it ripples across blocks, so it takes bigger strides. And we quickly choose from one of the two pre-computed outputs. So essentially, we get a time complexity which is k plus n by k, and we differentiate it and we find the optimal value of k to be square root of n, and thus the total time is order of square root of n. But essentially, all our benefits came from computing the carry very quickly. So let us thus focus on computing the carry without actually performing the addition if required. So some kind of a shortcut to get rid of this carry business. So let's do one thing. So we need to define a little bit of algebra before we actually proceed. So let us consider two corresponding bits of a and b. So a and b are the two numbers that we are trying to add. We are trying to add a plus b, and both of them are n-bit numbers. So let's define a generate function. A generate function means that a carry is generated after the addition. So C out is equal to 1. On similar lines, let us define a propagate function. So basically, if I consider a block of bits, if irrespective of the input carry, we are generating an output carry, we say that the block is generating a carry. For example, let me consider this block 1 1 plus 1 1. Irrespective, so if I irrespective of the input carry, we will always generate an output carry. So input carry is 0. So 1 plus 1 will be 0, and this will be 1, and output carry of 1 will be generated. Let's assume that the input carry is 1. So 1 plus 1 plus 1 is 1, carry of 1, again 1, and a carry out of 1. So if this is the contents of the block, irrespective of the input carry, the output carry will always be 1. So we are saying that we are generating. Now let us define a propagate function. So the propagate function says that the output carry is equal to the input carry. So let's consider the example. So let's consider a single bit example, which will be far easier to understand. So let's consider the values of ai and bi. So let's consider multiple values. So let's assume these are 0 and 0. If they are 0 and 0, and let's consider the carry, irrespective of the value, so let's consider the carry in. Irrespective of the value of the carry in, the carry out will be 0, right? So even if the carry in is 1, we'll still not generate a carry. If it's 0, we'll still not generate a carry. Now let's assume, now assume that ai is 0 and bi is 1, right? So in this case, yes, so in this case, let's see. So let me maybe draw a quick line here to demarcate. If the input carry is 0, then the output carry is 0. But if the input carry is 1, then we are adding 1 plus 0 plus 1, which is 1 0, right? So the output carry is 1. So what we can clearly see is that the output carry is the same as the input carry. Now let's consider one more example. In this case, let AI be 1, let BI be 0. And let's assume that the input carry is 0. If the input carry is 0, we are adding 0 plus 1 plus 0. No carry is being generated, so the output carry out is 0. If, however, the input carry is 1, then we are adding 1 plus 1. The sum is 0. The carry out will be equal to 1. Hence, the output carry will be equal to 1. So in both of these cases, the carry out is equal to the carry in. In the first case, irrespective of the carry in, the carry out is 0. So let's consider the last case. In this case, AI is 1, BI is 1. Irrespective of the input carry, so let's assume that the input carry is 0. So then we add 0 plus 1 plus 1, the carry is generated. Let's assume carry in is 1. So we add 1 plus 1 plus 1. Again a carry out is generated. So irrespective of the input, irrespective of C in, C out is always 1. So what we can say is that if AI and BI both of them are 1, which is when AI and BI is true, we can say that this combination of bits or this block, right, which has one bit of A and one bit of B, is generating a carry. So when do you generate a carry? You generate a carry when, irrespective of the input carry, you always generate an output carry. That will happen if AI is 1 and BI is 1. So I can define a function gi which is AI and BI. So if gi is true, means that a carry is always generated. Now let's consider this case when AI is 0, BI is 1, or AI is 1 and BI is 0. So how can I represent this case? The way that this case can be represented is by AI exclusive OR BI. So if you go back to our discussions in chapter 2, the XOR function. So let me just do a quick recap of the XOR function. We have anyway seen that many times. So the XOR function is 1 when AI is 0, BI is 1, or AI is 1, BI is 0. That's when AI exclusive OR BI is 1. In the remaining cases it is 0. So when AI exclusive OR BI is true, we can say that the carry is being propagated. What does propagation mean? Propagation means that the carry output is equal to the carry input. So if carry in is 0, then carry out C out is 0. If C in is 1, then C out is 1. So that's when the propagate function will be true. And if both AI and BI are 0, then irrespective of the carry in, the carry out will be 0. So in a sense, the carry is being absorbed. So what is the takeaway point from this slide? The takeaway point from this slide is the generate function that we have defined, which is AI and BI, means irrespective of the carry in, a carry out is always generated, and PI, which is propagate I, which means that this function, if this function is true, it means that the carry out, C out, is equal to C in. So keeping this in mind, let's move forward. So let's use the GNP, generate and propagate functions, for a bit pair. So the carry out can be said it is equal to GI. So plus means, so plus here means an OR and dot means an AND. So this is, so if GI is true, then a carry out is definitely being generated. Otherwise, or the carry input is true and the propagate is true. So there are only two ways that Cout can be 1. Either the block is generating a carry, or the block is propagating a carry and the carry input is 1. So we can say it is Gi or Pi and carry input. So let's consider an example. Let's say Ai is 0, Bi is 1. Let the input carry be Cin, compute Gi, Pi and Cout. So Gi is Ai and Bi, which is 0 and 1, which is 0. So this is not generating. Pi is Ai XOR Bi, which is 0 XOR 1, which is 1. So it's propagating. So Cout is Gi plus Gi or Pi and carry input. So this is 0. It's propagating. And we don't know the input carry, so we can say Cout is equal to Cin in this case. So let's now consider a multi-bit system where a block does not have one bit each of A and B, but it has multiple bits. So let's define some simple terminology first. So let's say that Cout I means the output carry for the ith bit pair. Similarly, let's say Cin I is the input carry for the ith bit pair. Similarly, Gi is the generate value, the generate function for the ith bit pair, and Pi is the value of the propagate function for the ith bit pair. A bit pair is a pair of bits, so when you are adding, we have multiple bits of A and multiple bits of B, right? So one corresponding pair of bits is called a bit pair. So now let's write some basic equations for multi-bit systems and let's see what it looks like. So let's say we have already derived this, that for the first bit pair Cout1, it is G1 plus P1 times the carry that is, so no, not times, P1 and the carry that is coming in, which is Cin1. Now let's consider the second bit pair, which is, so basically let's consider the two bits A2 A1 and B2 B1. So basically for the first bit pair, this is the equation, right? This is the equation for the first bit pair. If I consider the second bit pair over here, the carry that is coming out, Cout2, is G2 or P2 and the carry that is coming out of the first bit pair. So then I can do a little bit of algebra and replace Cout1 with this expression here, which comes to here. And I just rearrange the terms. So what I see is that for finally I have Cout2, which is the carry which is coming out from this as Cout, and the carry which is going in, which is Cin1. So I finally have an equation in terms of Cin1 and the generate and propagate functions of the pair of bits. So so the way that the generate function for essentially the pair of bits, right? So I can think of this as one big block now, right? So for this block, the generate function is actually G2 or P2 and G1, and the propagate function is P1 and P2, which basically means that the input carry will show up in the output if every pair of bits is propagating it. So that's the reason for the AND function. And a nice way of understanding a generate is that either the last pair, the second pair, is generating, or the first pair is generating and the second pair is propagating, right? So this can be considered as the generate for the 2-bit pair and this as the propagate. So let's consider a 3-bit system. So we can write a similar equation that either Cout for at the end of 3 bits, either the third bit pair is generating or the third bit pair is propagating the carry generated out of the second, out of the addition of the first 2 bits. So then here for this equation we can substitute this result. After doing some algebra, we again come at this. So this is the generate function for a 3-bit system. So when will a 3-bit block generate? When either the third bit pair is generating, or the second bit pair is generating and the third bit pair is propagating, or the second and third bit pairs are propagating and the first bit pair is generating. And when will it propagate? It will propagate when all the 3-bit pairs P1, P2 and P3, all of them are propagating, so the input carry will reflect in the output. So similarly, we can have much more complicated algebra, but what you can see is that all of these are essentially following the same pattern, exactly the same pattern. So for a 4-bit system, the generate function looks something like this. The pattern is the same. So for a 4-bit block, so let's assume A4, okay, let me write it, A4, A3, A2 and A1 being added to So when will this actually generate? It will generate when either, this bit pair over here, let me use a laser pointer, it's easier. Okay, so when this bit pair over here is generating, which we see over here, or this bit pair is propagating and this bit pair is generating, or these two are propagating and the carry is being generated here, or all of these three are generating and a carry is being generated over here. When will a carry propagate across this block? When every single bit pair P1 and P2 and P3 and P4, all of them are propagating the carry. So in the same way, for an n-bit system, we can create a generate function and a propagate function. So let's take a look at the pattern. So coming to the pattern here, for a single bit block, Cout is G1 plus G1 or P1 and carry input, where is simple functions. For a 2-bit system, for a 2-bit block, we can see the generate function is slightly more complicated. The logic has been explained. And the propagate function is P1 and P2, which means both the bit pairs need to propagate. So we just keep going on and on. And for a 4-bit system, we can clearly see the generate function is more complicated. In the sense, either the fourth bit pair is generating, or the fourth bit pair is propagating and the third bit pair is generating, and so on. And when does a 4-bit system actually propagate? When all the bit pairs are propagating the carry, input carry to the output. Similarly, for an n-bit system, we can create a generate function and a propagate function, and given the input carry, we can find out the output carry. So now the idea is, can we compute the generate and propagate functions quickly? So let us look at some other results for the GNP function. So let us do one thing. Let us divide a block of n bits into two parts. So let's consider this block of n bits. So we divide it into one part is 1 to m and the other is m plus 1. M bits here and m plus 1 to n bits over here. Let the carry out and the carry in to this block be carry in here and the carry out here. So we want to find the relationship between the generate function for the entire n-bit block, the propagate function for the entire n-bit block, and the generate and propagate functions for these sub-blocks. So generate from 1 to m, propagate from 1 to m, generate from m plus 1 to n, and propagate from m plus 1 to n. What do they exactly look like? So let's take a look at this equation and try to work it out. So in this equation, so the carry out is essentially equal. So let's do one thing. Let's call the carry, which is propagating from, let's say, the sub block of the first m bits to the remaining n minus m bits as C sub, right? Let's refer to this carry as C sub. So the final C out, the carry out, is the generate of m plus 1 to n. So this block, so final carry out, how will we compute? Either this simple block over here of n minus m bits, either this is generating, in that case we'll have a carry out, or it is propagating the carry that has come from its right, which is C sub. That's the only two ways in which we can get carry out. So carry out will be G m plus 1 n or P m plus 1 n for those n minus m bits ANDed with C sub. So either you are generating or you are propagating, right? There is no other way to generate a carry. So there is no other way for carry out to be 1. So you do a little bit of algebra. We'll keep G m plus 1 n and this C. So what is C sub? C sub is basically the carry out of this other block over here consisting of the first m bits. So we can write that as, so when will its carry out be true? When either it is generating a carry G1 to m or it's propagating the carry input, and so which is P1 to m ANDed with carry in. By doing a little bit of algebra and rearranging the terms, what we see is that the generate function from 1 to n will essentially be the generate function of the first n minus m bits or the propagate function's value for the first n minus m bits and the generate function the first 1 to m bits, which means that either the first 1 to m bits is generating a carry and the carry is being propagated through the n minus m bits, or the n minus m bits are generating a carry and the carry is being reflected in the carry out. That's the only two ways. So what we can write ultimately, C out is G1n plus or P1n and C input, where the generate function for the n bit system can be represented as a function of the generate and propagate functions of the first m bits and the remaining n minus m bits. So the important equations that we get from this particular section over here is that generate 1 to n. So basically the first 1 to n bits, so consider a block of the first 1 to n bits. When will it actually generate a carry? It will generate a carry if the bits from m plus 1 to n, the rightmost subblock, if that is generating a carry, or if if this subblock over here from the last n minus m bits, if that subblock is propagating and the other subblock consisting of the first m bits is actually generating a carry. So that is pretty much the two ways in which a carry can be generated from the n bit block. So let me explain this in a different way. So let me consider n bits. We are dividing it into two subblocks. So one subblock consists of the bits from m plus 1 to n, and the other subblock consists of the bits from 1 to m. We have a carry input and we have a carry output. So let's try to understand this particular equation slightly intuitively. So when will the carry output be actually 1? The carry output will be 1 if the entire block of n bits either generates a carry, which means irrespective of the carry input, the carry output will be 1, right? Or the entire subblock or the entire block from 1 to n propagates the input carry, and the input carry, if it's 1, carry out will be 1. So basically for the generate function of 1 to n bits, so when will this n bit block actually generate a carry? It will generate a carry if, let's say, this block, so let's call this left block and let's call it right. So when the left block over here is generating a carry, or the left block from m plus 1 to n is propagating a carry, and the right block is generating a carry. So in this case, a carry will be generated and will get propagated till the end. Now, when is the n-bit block actually propagating a carry? It is propagating a carry when, so essentially carry comes here and it sort of gets propagated till the end. This will happen if both the blocks, the left one and the right one, both of them are propagating a carry. So the propagate function will be p m plus 1 to n ANDed with p of 1 to m. So which is a similar logic that we used when we were writing the equations for multi-bit systems. And so this is also one way of writing the equation. So we shall find it very handy when we discuss a carry lookahead adder. But the important take home point over here is that a carry out is generated only under two circumstances. The circumstances is that either the n-bit block generates a carry, which means irrespective of the input carry, the output will always be 1, or when it propagates a carry, which means that if the input carry is 1, the output carry will be 1, and if the input carry is 0, the output carry is 0. So the problem that we wanted to solve over here is that given an n-bit block, can we represent its generate and propagate functions in terms of the generate and propagate functions of the different sub-blocks, the left one and the right one? We were able to do that, and these are the two equations to do that. So the take home point here is that the generate function for the entire block is essentially the generate function of the n minus m left bits ORed with the propagate function of the n minus m left bits with the generate function of the m right bits, and the propagate function for the entire n-bit block is essentially the AND of the propagate functions of the individual subblocks. Now let's give an insight of computing the generate and propagate functions quickly. So the idea is that we can compute GNP for a large block by first computing the generate and propagate functions for smaller subblocks. Then we can combine them using these equations to actually so if you see this diagram, we have the generate and propagate functions for smaller subblocks, and these have been combined to create the generate and functions for a larger block. And once we have that, we can let me just clean the screen of annotations 1 second. We can then use this equation to sort of, given the carry in, compute the carry out, right? So then, so what's the idea? We take smaller subblocks, compute their GNP functions. We combine the solutions for the smaller subblocks to find the generate and propagate functions for a larger block, and so on and so forth. So a fast algorithm to compute GNP will have to use some sort of a what is called a divide and conquer strategy, which means first solve the problems for very small blocks and gradually combine it to get the solutions for bigger and bigger blocks, right? So basically this we want to do in order log n time. Let's see how. So the carry lookahead adder is similar to the carry select adder in the sense there are two stages. So in stage 1, we compute the generate and propagate functions for all the blocks. How do we do it? We combine so first we find the solutions for GNP functions of all the single bit pairs. We combine the solutions to find GNP functions for sets of 2 blocks. Then we combine the solutions to find GNP functions for sets of 4 blocks, and so on. So basically, 2 blocks means 2 blocks of bits. So basically, what we do, let me explain this. If we have A and B, and A contains 32 bits, B contains 32 bits. So let's consider each bit pair. So what we do is initially we compute the generate and propagate functions for each bit pair. And then what we do is that we sort of create a multi-bit system where we compute it for two blocks, right? Uh, Two blocks, or let's say or two bit pairs. And similarly, we combine the solutions to find GNP functions for sets of 4 bit pairs. So I should maybe make it bit pairs. It's slightly easier to understand. So similarly, we just keep on increasing the size of each block, okay, the number of bit pairs in each block. And so finally, so what do we do? So if we start out with assuming that A has 32 bits and B has 32 bits. So we start out in a parallel fashion by computing the GNP functions for each pair of bits. So at this point, each block contains one pair of bits. Then what we do is that we combine, for let's say A1, A2, A1, B1 and A2, B2, we combine the solutions to get the solution for a 2-bit system. Then we take all the solutions for 2-bit blocks and we get solutions for 4-bit blocks, right? Solutions means GNP functions. Then we combine the solutions for 4-bit blocks and then we get for 8 bits. Then from 8 and 8, 16, and finally 16 and 16, 32. So we find the GNP functions for a block size of 32 bits at the end, right? For a block of size 32 bits means 32 bit pairs. So also, I would, instead of writing blocks here, I would rather say, for 2-bit pairs and 4-bit pairs. So basically at the end of this exercise, what is it that we have? We essentially have G32 and P32. So what is the final carryout? The final carryout of the 32-bit addition is G32 ORed with P32 and the carry in, if there is a carry in, right? So that is the simple equation that we have. And so this is essentially, so what do we get in stage 1? What we get in stage 1 is that we sort of create a hierarchy and we consider larger and larger block sizes and we compute their GNP functions. So this is shown in this diagram. So in this diagram, what we do is that so let's do one thing. So let's number the bit pairs, first bit pair, second, third, fourth, and so on. So let's say that in level 0 we consider 2 bit pairs. Can be done. We have the solutions for a 2-bit system. So we compute the GNP functions for the first 2 bit pairs, which is 1 to 2, 3 to 4 till 29 to 30, and 31 to 32. So this is level 0, this is level 1. In the next level, what we do is we compute the GNP functions for a 4-bit system for 4-bit pairs from 1 to 4. Similarly, another groups of 4 and so on. So at this point, so we actually have 16 bit pair, we have 16 blocks. At this point we have 8 blocks. Then what we do is we take those 8 blocks and coalesce them into 4 blocks by computing the GNP functions from bit pairs 1 to 8, GP functions from 9 to 16, GP functions from 17 to 24, and 25 to 32. And then we again coalesce them to find the GP functions from bit pairs 1 to 16 and GP functions from for bit pairs 17 to 32. And then finally we compute the GP function for the entire block of 32 bits, right, which is from 1 to 32. So basically there are two important points that we need to understand here. So this thing can be done, and mind you, in each level all of these computations are happening in parallel, right? They are not happening in series. So hardware by definition is parallel. it is not in series. So pretty much in level 1, so we will have many of these hardware circuits that will be computing the values of the GP functions for the for the bit pairs in parallel. So this all of these things will happen simultaneously at the same time. Can happen in the same time. There is no dependency per se between these circuits, and there will be 16 of such circuits. So for example, the GP circuit here will compute the GNP functions for the first two bit pairs, this for the third and fourth bit pairs, and then we gradually we shall merge. So the GP function here will take the GP functions of this unit and this unit and merge them as per this equation, right? Can easily be done as per these two, right? So what needs to be done? You need an OR gate and an AND gate, very simple. And in this case, you need only an AND gate. So these are simple computations. Similarly, this block will take the inputs from this circuit will take an input from this circuit and another circuit here, and we'll just keep on doing this. And at every point, for the propagate function, we need to do an AND, and for the generate function, we need to do a single OR and a single AND. So what we can say is that for each level, the time that it takes is the time that any one of these circuits take, because all of them are working in parallel, and they take roughly order of 1 time, which means constant time. So this also takes order of 1 time, and so roughly all of them, since they're the same circuit, take the same time. So the total time that you require is essentially order of the number of levels, right? So how many levels would you have? The number of levels we will have, so consider the fact that we have 32 bits, and at each level the number of circuits, so we start from 16 because we are considering maybe in this case 2 bit pairs at the same time. So we start with 16 and then go half of that, 8, 4, 2 and 1. So the number of levels, since we are decreasing by 2 in every in every layer, right, in every level, the number of levels is basically order of log n to the base 2. So in computer science, whenever we say say that a number is of the form log n, we typically mean it is log n to the base 2. So that's the reason this can be written as simple as order of log n. But in any case, log n to the base 2 or base 10 or base 100 does not matter, because log n to the base 2 and log n to the base 50, they only differ by a constant factor, which anyway the order notation takes care of. So the base does not matter, it's just order of log of n. So essentially computing this part, the GNP functions for blocks of bits, starting from consecutive bit pairs to 1 to 4, then 5 to 8, 9 to 12, 13 to 16 and so on, and then blocks of 8, blocks of 16 and the entire block of 32 will essentially take order log n time, because for each level we do a constant amount of work, right? One AND for the propagate and one OR and one AND for the generate, and we have order of log n levels, so the total time it will take is order of log n. And we will have essentially in a tree of GP functions, like in an inverted triangle, for different, we'll have GNP functions for different ranges of bits. So the question is, we need to use it to actually do our addition.